In this problem, we will use the steam tables to help solve an open system entropy balance. And so in this problem, we're dealing with a process in which we are mixing a stream composed of superheated steam at this mass flow rate, pressure, and temperature, and it's going to be mixed with an equal mass flow rate of saturated steam at this pressure. And we're told that the saturated steam has a steam quality, and I made a typo here and corrected it. The steam quality is going to be 0.05. And so from the mixer, so emerging from it, the outlet, we also get saturated steam that's going to be at a pressure of 0.5 megapascals. And so for this process, we want to determine what is the mass quality of the emerging steam, how much entropy is generated by the mixing, and then as a sort of hypothetical question, we want to determine if we could actually do the reverse process spontaneously. And that is, take some sort of steam and then split it into the original two streams. Based on the information in this problem statement, I want you to pause the video here and sketch out the process flow diagram. Based on the information in this problem, we could sketch out a process flow diagram that looks like this. We have our superheated steam and we have our saturated steam, and we mix them together to form an outlet stream of saturated steam. For the inlet saturated steam, which I call stream 2 here, we're told the mass quality, which is 0.05, and remember, mass quality just means the mass fraction of steam that's in the vapor phase over the entire mass of that steam, right? And so in order to calculate the mass flow rate of the vapor component of the saturated steam, we just take the mass quality, multiply it by the total mass flow rate, and it gives us this value. To find the liquid fraction, we just take 1 minus that mass quality. Okay? All right, and so in this problem statement, what we want to figure out are the mass quality of the outlet steam, the entropy generated by the process, and then we want to see if the reverse process is spontaneous. Okay? And so before we begin this problem, let's list out some assumptions that we're going to need. And so because we're dealing with 5 unknowns, that means we either need 5 equations or in total we need 5 equations and pieces of information in order to solve for all of the unknowns. And specifically, because we're dealing with steam, that should be a very strong hint that we need to use the steam table to help solve this problem. And so we're going to be going through the steam tables in a bit. In any case, as far as assumptions are concerned, we're dealing with an open system. And because nothing is changing with time, we're going to assume it's operating at steady state. Because we're dealing with steam, that should tell us we need to use the steam tables. We're not going to worry about changes in kinetic or potential energy. And then based on this problem statement, we're also not going to worry about any sort of heat term. Right? And there's no moving parts, there's no, even though we're using a mixer, it doesn't really give us any information about, any sort of impeller that's strong enough. So we're not going to worry about shaft work either. Okay. Because we're using steam tables, that means our reference conditions are going to be the same reference conditions as the steam table. Okay? All right? So using those assumptions, let's proceed through our balances. So our material balance accumulation is equal to input minus output plus generation minus consumption. We're not dealing with any reaction, steady state. Therefore, our inputs are equal to our outputs. Our input term is equal to the sum of the mass flow rates of stream 1 and stream 2, and our output is just stream 3. Therefore, we know that M3 is just the sum of M1 plus M2. And if we add those together, we get 10 to the 4th kilogram per hour. Right? So that's the overall mass flow rates. But what's a little bit more useful here is to actually consider the mass flow rates of the vapor and liquid components in each of the streams. Right? If we go back up here, we know that stream 1 is superheated. And so what that means is it's entirely in the vapor phase, and so its mass quality is equal to 1. Right? So this entire stream 1 is in the vapor phase. For stream 2, however, we're told that the mass quality is this value here. Okay? And so if we think about stream 2, it's actually the M2 is going to be the sum of M2V and M2L. For M2V, we could relate that to the overall mass flow rate by multiplying M2 by the mass quality. And for the liquid component, we just multiply by 1 minus that. Alright, similarly for stream 3, we're told it's saturated, and in the end we want to figure out the quality as well. And so for stream 3, we could also split it up into the vapor and liquid components, such that M3V is equal to Q3M3, M3L is equal to 1 minus Q3 M3. Okay? Alright, so from our material balance, we could write out these relationships. Let's now move to the energy balance. Open system, so we write the open system energy balance. HI hat plus 1/2 velocity squared plus the potential energy. Left hand side is 0 because it's steady state. We're not worrying about Q. We're not worrying about shaft work. Don't need to worry about kinetic or potential energy. And so really what we're left with is we're just only dealing with the enthalpies of the streams going into and out of the system. Okay? And so left hand side is 0. And for the right-hand side, I'm going to split this up so that we write the enthalpies in terms of the enthalpies due to the vapor phase and the enthalpies due to the liquid phase. For stream 1, it's only in one phase. But for stream 2, we have the vapor component and the liquid component. For stream 3, we have the vapor component and the liquid component. Okay. I'm then going to rewrite these in terms of the steam qualities, or the mass qualities, I mean. M2, well, let me write it as Q. Q2, M2, H2V plus 1 minus Q2, M2, H2L minus 1 minus Q3, M3, H3V. Well, that's not 1 minus Q. This one is just Q3. And this one's 1 minus Q3, M3, H3L. Okay? Alright, so we have this somewhat lengthy equation, but when we look at it, there's only really one unknown that we're dealing with, Q3. And so in order to solve for that mass quality, which the problem asks us to solve for, all we have to do is just look up all of the different enthalpy values. And then we'll be able to solve for the mass quality. So I'm going to call this equation 1 here. So I'll write this out. If we can figure out h sub i's, we can solve for Q3. Okay? And so to figure out all our enthalpy values, let's go to the steam tables.